These are the final numbers that I ended up getting for the different conformations that we just analyzed. Your numbers may or may not be exactly the same, and they don't have to be exactly the same. I'm just showing you kind of what I got. What I'd like to do now is determine the difference between each of these. So we're going to go ahead and take the difference between the axial and the equatorial energy values by typing equals, setting it equal to this cell, and then subtracting the other cell. We'll go ahead and copy this down. You can see that the largest difference or energy difference is going to be in the tert-butyl cyclohexane group. That is, there's the largest energy barrier between axial and equatorial for this molecule than for the other ones. There is a slightly larger barrier for the isopropyl substituted group than the methyl one. Let's see if that holds true or is consistent with data that have actually been experimentally reported. We'll do that by turning to table 4.10 from our text. Here is that table. As you can see, a methyl substituted cyclohexane has a KEQ, that is an equilibrium constant value of 18. What that means is that there's an 18-to-1 ratio of equatorial to axial of that molecule. So energetically speaking, the equatorial, as we would predict, is much more favored. That number shoots up to about double for the isopropyl group, with a ratio of 35-to-1 favoring the equatorial over the axial. You'll see that as you go to the tert-butyl group, that ratio goes even higher, with the KEQ being 4,800. So in real life, tert-butyl cyclohexane will favor the equatorial conformation over axial by a ratio of about 4,800-to-1. Let's go back to our data and see if our calculated data are consistent with these reported data. Once again, you can see that our calculated data show a difference of 6.17 kcals per mole, favoring the equatorial over the axial for the tert-butyl substituted cyclohexane, which compares with a 1.65 kcal difference for the isopropyl cyclohexane, which compares with a 1.29 kcal difference for the methyl cyclohexane. Now, I grant that the differences here are not as large of a difference as we see from the data in our table. That is, for the tert-butyl cyclohexane, I would expect that number to be much, much larger predicted using the software than what the KEQ value is of 4,800. Why isn't it so much larger? Well, the reason is because in order to convert from an equatorial to an axial and vice versa, the molecule actually has to undergo some different shapes in between. We haven't calculated the energy levels of all of those intermediary shapes. If we did that, we would probably find that there are some of those that are extremely high in energy, much higher than either the equatorial or the axial, and that the shape change between the two have to traverse that high energy hill. I hope that makes sense. So for your assignment for this lab, what I want you to do is to draw each of these molecules and get your own energy levels calculated using the Viewer Pro software for these three compounds, methyl, isopropyl, and tert-butyl cyclohexane. Once you have calculated the energy difference between the predicted equatorial and axial conformations, I then want you to compare those to the KQ values that I just showed you on the table and write it all up in a beautiful little report with cute little pictures and things. I'd then like you to write an explanation as to whether or not our data follow what the table predicts, and if there are any discrepancies, why. The assignment will of course be due on the date marked on our course syllabus. That's it for this one, students. Until I see you guys next, have an enjoyable rest of your day.